Lecture. I am Dr. A.VELMURUGAN, Assistant Professor, Department of Mechanical Engineering, Government College of Engineering, Chettikari, Dharmaburi. In this video lecture from upcoming semester Thermal Engineering 2, Unit 3 Steam Turbine, Module 2. Previously, we have discussed about the Module 1, Introduction of the Steam Turbines, Application of the Steam Turbines, Classification of the Steam Turbine. In this module, we have discussed about the compounding of the steam turbines. The main objective of the compounding steam turbine is the same output is which reduced from the revolution per minute, because the single stage turbine there is a high RPM. We have to, with the help of this compounding steam turbine, to alter the output, but to reduce the speed it can be used for the power generation. From this slide we have discussed about the compounding of the steam turbine. If the high velocity of the steam is allowed to flow through one row of moving blade, it produces a rotor speed at about 30,000 rpm, which is too high for practical use. Previously I told about you from the D level turbine. From the D level turbine is a single stage turbine. The blade RPM is 30,000 rpm. We have to reduce the speed with the help of these compounding turbines. From this compounding turbine there is a different stages: fixed blade, moving blade, fixed blade, moving blade. It is therefore essential to incorporate some improvements for practical use and also to achieve high performance. This is possible by making use of more than one set of nozzle and rotor in a series, keyed to the shaft, so that either the steam pressure or jet velocity is absorbed by the turbine in stages. This is called compounding of the turbine. The high rotational speed of the turbine can be reduced by the following methods of compounding. First one is velocity compounding, second one pressure compounding, third one pressure velocity compounding. From this slide we have discussed about the velocity compounding, that is a Curtis turbine. From this figure we have discussed about, here the velocity compounding only is a single nozzle, moving blade, fixed blade, moving blade. From the nozzle the high velocity steam is entered to the nozzle, it goes to the moving blade. From the moving blade the velocity will be decreased. From the fixed blade the velocity will be, there is no changes in the velocity. Again the steam is goes to the moving blade, that time the velocity will be decreases. From the graphical representation, already I told about you, from the nozzle, from this Curtis turbine or D level turbine, there is a single nozzle. From the nozzle the pressure will be drastically reduced. After the blade there is no any changes. From here we have to see about the pressure of steam is from here. After the nozzle the drastically the pressure will be reduced. After that moving section of the moving blade, there is no any changes in the pressure changes. It is goes to the condenser pressure, that is at 0.014 for the atmosphere. From that velocity of the steam is entering to the nozzle, the high velocity of the steam is rises up. From the moving blade it will be, the velocity will be decreases. From the fixed blade there is no any changes from the nozzle. Again the steam is goes to the moving blade, again the velocity will be reduced. From the D level turbine the velocity will be reduced from 10 to 12 percentage. From that kinetic energy is reduced. The velocity of the inlet velocity of the steam is 1100 meter per second. The low last from this here, from this portion to from this portion the velocity will be reduced. But if using this velocity compounding, the the velocity will be reduced from 1 to 2 percentage. From this Curtis turbine that consists of some set of nozzles and a fixed row of moving blades which are fixed to the shaft, and rows of fixed blades which are attached to the casing. As shown in figure, the two rows of the moving blades are separated by a row of fixed blade. The high velocity of steam first entered to the first row of the moving blade, where some portion of the velocity is observed. Then it entered to the ring of the fixed blade. There is no any changes in the velocity. From the second fixed blade there is no changes, velocity steam passes over the fixed blades. Again the steam is going to the moving blade, again the velocity will be reduced. Thus the fall in velocity occurs every time when the steam passes over the row of moving blade. The steam thus leaves the turbine with low velocity. The variation of the pressure and velocity of the steam as it passes over the moving and fixed blade as shown in figure. It is clear from the figure the pressure drops takes place only in the nozzle section and there is no further drop of the pressure as it passes overing the moving blade. Already I told about you from that pressure drop only occur in the nozzle section. From the blade section there is no any changes in the pressure drop. This method of velocity compounding is used in the Curtis turbine after it was first proposed by the C.G. Curtis. Next slide we have discussed about the advantage of the velocity compounding. The arrangement has less number of stages and hence less initial cost. The arrangement requires less space. The system is reliable and easy to operate. The fall of pressure in the nozzle is considerable, so the turbine itself need to work in high pressure surroundings and the turbine housing need to be very strong. From the disadvantage of the velocity compounding turbine, there is a more friction losses due to very high velocity in the nozzle. Less efficiency because the ratio of the blade velocity to steam velocity is not optimum condition. The power developed in the latter rows in only the fraction of first row. Still, at the stages require same space, material and cost. Next slide we have discussed about the pressure compounding turbine. From this pressure compounding turbine is a from this pressure compounding turbine there is a two nozzle, there is a blade. From this pressure compounding turbine the high velocity steam is entered to the nozzle. From the graphical representation from this pressure entering the steam in the nozzle section there is drastically the pressure drop will be reduced. From the blade section the pressure will from the blade section there is no any changes from the blade section from the pressure after it goes to the steam is goes to the nozzle section again the pressure will be reduced. Again it goes to the blade section, there is no any changes from the pressure of the steam leaving from the section. From this pressure drop from the nozzle section is reduced. From the nozzle section the pressure drop will be reduced. From the blade section there is no changes in the blade section. Simultaneously from the velocity of the steam is entering to the nozzle, the high velocity steam is will be raised from the nozzle section. From it goes to the steam is goes to the blade section, again the velocity will be reduced. Again the steam is goes to the nozzle section, the velocity will be increased. After it goes to the steam is goes to the blade section, the velocity will be reduced. This is the graphical representation. It will clearly show from the velocity of the steam entering, velocity of the steam leaving from the pressure compounding turbine. From this turbine it consists of number of fixed blades which are incorporated between the rings of moving blades. The moving blades are keeled to the shaft. Here the pressure drop is done in a number of stages. Each stage consists of a set of nozzle and a ring of moving blades. Steam from the boiler passes through the first set of nozzle where it expands partially. Nearly all its velocity is observed when it is passes over the first set of moving blades. It is further passed to the second set of fixed blade where it is partially expand again and through the second set of moving blades where the velocity of the steam is almost observed. This process is repeated till steam leaves at condenser pressure. By reducing the pressure in the stages, the velocity of the steam entering the moving blade is considerably reduced. Hence, the speed of the rotor is reduced. This type of turbine is a Rative or Zoli turbine. Used this method of compounding for the Rative turbine is suitable for the pressure compounding turbine. In this method of compounding, the both pressure and velocity compound methods are utilized. The total drop in the steam pressure is carried out in two stages and the velocity obtained in each stage is also compounded. The ring of nozzles are fixed at the beginning of the each stage and the pressure remains constant during the each stage. This method of compounding is used in the Curtis and Moore turbine. Next slide we have discussed about the pressure velocity compounding. From this pressure velocity compounding there is two sections, from left hand side one turbine and right hand side one turbine. From the left hand side turbine there is a nozzle section, moving blade, fixed blade, moving blade. From the right hand side nozzle section, moving blade, fixed blade, moving blade. From this turbine how to the pressure drop will be reduced and the velocity, how to the velocity will be increasing from the steam entering section, and the velocity will be reduced from the velocity of steam leaving section. From here the pressure of the steam is entering from the nozzle section, the pressure drop will be reduced from the nozzle section. After the pressure will be remain same in the moving blade and fixed blade section. Again the pressure drop in the nozzle section from the right hand side of the turbine, the pressure drop is happen on the nozzle section. From that after that the pressure will be same at the moving blade and fixed blade moving blade section. Simultaneously from the velocity of the steam is entering to the moving blade section, from the nozzle the pressure will be the high velocity of the steam is entered to the moving blade. From the moving blade the velocity will be decreased drastically. After that it goes to the steam is goes to the fixed blade, there is no any changes for the velocity distribution. Again that steam is goes to the moving blade, again the velocity will be decreased from that portion. Again that steam is goes to the right hand side of the turbine, the pressure the velocity of the steam is will be increased from the nozzle section. Again the moving blade the velocity will be decreased. From the fixed blade there is no any changes. Again the goes to the steam is goes to the moving blade, the velocity will be decreases. Based upon this pressure velocity compounding turbine is with the major output, there is no any changes for the output, but the ultimate aim is we have to reduce the speed of the turbine, and also it is used for the power generation. It is used for mainly used for the power generation. Previously I told about the D level turbine is single stage turbine, it will be rotating for the 30,000 rpm. The power output is there is no any changes. If you using the compounding of the turbine means the output is same, output will be placed on the turbine, but we have to reduce the speed of the blade with the help of this pressure compounding, velocity compounding, pressure velocity compounding. Thank you.